Good day to you. This is ANAGALACTIC bringing you the second in our special series on Imaginarity. Are we really dealing with imaginary things? It's relative, and that is the perfect seg. And imaginary, just what is meant by that? Well, we covered the basics of that in the last lecture with the 2D imaginary axis, which we got down to its geometric formulation, which is important to be able to visualize. I don't think this is taught very clearly very often. Just what is the complex plane and why is it so valuable? So what is space-time geometry? You begin looking at the situation from his point of view. The definition of gravitational relation cannot be formulated without incorporating the time differential over a sufficient volume of space in which he's trying to compute gravity to get a formula for it, improving on Newton's formulation by incorporating the time differential. That Newtonian gravitation works because the time differential does not appear measurably in Earth-side computations. But it's not adequate for cosmic space because the volume is larger, and now simultaneity becomes an issue. And without going into tremendous detail on that aspect of it, my purpose here is to give you a clear perception of the geometry of space-time, which begins with the usual cubic system. So it is linear. A single line is, of course, a 1D linear space of one dimension. That's what 1D means. 2 means you now have square space. And when you add the third, that fills space cubically, which gives you an excellent grid. But if you're attempting to compute sphericity, but when you begin with cubic space, you need imaginarity in the complex sense, because what imaginarity does is it gives you the circular function in the space, that is the normalized curvature function, which in 2D space would be a circle, but in 3D space is a sphere. What this leads to is two things which are not good, but it does two things that are just extraordinarily difficult to intuit what is happening, because we're used to 3D cubic space, but now to get the spherical function, one needs to introduce an imaginary axis. On the 2D plane, that was easy. There's only one extra axis, and that works to create a circular function. But in 3D space, when you add the fourth, or it has to be orthogonal, because everything depends on the Pythagorean theorem in 2D and 3D, to get that spherical function into the 3D cubic system, the fourth axis has to be negative. And for the same reason that the square root of a negative number is used, to get an orthogonal reflection on the plane, whereby the square root of -1 basically goes in as the square space goes out. So you have a reciprocal function, which if you use the base of E, it normalizes the relationship between the x and the y-axis, which makes a perfect circle. Now what Einstein needed was to create a perfect sphere, because gravitational space is spherical. It will have a center of gravity. So he did the same exact trick, but with a 3D basis instead of a 1D basis. The horizontal line for the 2D, the beginning of the 2D system, can be given an imaginary axis, which creates the reciprocal relationship between the two lines, so that the vertical axis is actually inverted. It's an inverted index on the square root of -1 instead of the positive square of 1. So one basically goes in as the other one goes out, and that orthogonalizes the circle in a certain relationship that works. It creates the circular function. Now, for Einstein to get the spherical function, the imaginarity of the fourth axis has to be applied to all three of the cubic axes. The relationship is established between the imaginary time axis, he called it time, but he made it imaginary in exactly the same way that the y-axis is made imaginary in 2D space. So I hope that gives you a good introduction to the nature of space-time. Curvature is generated by the imaginary axis, which introduces the spherical function into cubic space. That might strike you as extraordinarily inefficient. That is the basis of my further inquiry into the nature of the basis space, because it should not be cubic if we could use spheric geometry instead. That will be in the next lecture. The discoveries that I made in the basis of mathematics, algebra, and geometry, in the solutions that we need for spheric phenomena and the quantum mechanical paradox, is actually the inner limit to the same proportion that physical infinity is the impenetrable outer limit, because we cannot compute something that we do not have a bound for. So the Big Bang is highly questionable because it is a linear solution, and it does rely ultimately on zero. The center of the linear system is a zero. That turns out to be the problem. And it's also the problem at the quantum limit, that we cannot get to what we think, or what we're forced to think, is the zero at the center of the space. Does not exist. It can't be reached. To the same proportion that the edge of infinity cannot be reached, the inner edge of what we call space, manifested by the proton, creating a spherical space, that is a limit. So stay tuned for our next lecture, where we'll have the geometry and mathematics and algebra for space-time in a new space that's never been used by science, spherical space. It would need to have a number system. That is exactly what I discovered, is the proportional number system of spheric space. And it all relies on something called imaginary space. So that will be the capper for this first 3 issues of these lectures. Thank you for tuning in, and this is ANAGALACTIC bringing you the secrets of the universe in this special presentation that will run through Thanksgiving. Today is the 18th day of November 2023 from Chico, California. Thank you again. We'll be right back.